Frontier AI models operate under a severe structural limitation. They are stochastic pattern matchers, constantly guessing the next pixel or sound wave based on statistical probability. To produce a coherent output, these diffusion models require multiple steps of iterative denoising. They start with pure noise and repeatedly calculate updates, slowly resolving that chaos into a recognizable image or sound. This multi-step calculation introduces unavoidable latency. There is no instantaneous inference because the model must travel a nonlinear mathematical path before it can output a final frame. Because of this computational lag, creating a system capable of real-time musical improvisation, where an AI reacts instantly to a human playing an instrument, remains an unsolved challenge for standard generative architecture. To achieve zero-latency interaction, world models must abandon stochastic approximation. They need to transition to deterministic, physics-based simulation. Solving for this latency allows an AI model to transition into a state of continuous learning, responding to inputs as a deterministic physical simulation rather than a probabilistic guess. To build an architecture capable of this, we have to examine the biological root of spontaneous creativity. In contact improvisation, two bodies lean into each other, establishing a shared center of gravity and reacting instantly to micro-shifts in mass and inertia. This physical relationship is an example of metastability. The system is not at rest. It is in a highly energized state of balance, loaded with potential energy and ready to be set into motion. This view of the piano keys and internal hammers illustrates that same mechanical state. A virtuoso's resting finger operates in a delicate balance of flexor and extensor tension. It is a highly charged, non-zero state of readiness. The decision to strike the key triggers the quantum pulse. It is the exact, discrete microsecond a finger applies mechanical force, breaking the metastable balance and transferring kinetic energy into the instrument. Creativity, in this physical context, is the instantaneous collapse of vast musical knowledge into a single, perfectly calculated kinetic vector. To eliminate AI hallucination, we apply an architectural framework called the de Cesare protocol, or VITA-VQ. This protocol forces a generative model to obey strict physical laws. This schematic outlines the first step, establishing a zero-ground state. We anchor the AI in a mathematically fixed baseline, where every action derives from a specific input trigger. The discrete kinetic vector, the physical impact of the hammer strike, serves as the absolute starting point. Standard video models attempt to statistically infer how an object should move across the screen based on millions of past examples. They guess the trajectory. Injecting a ground truth physical axiom into the model removes that guesswork. It drops the system's variational free energy to zero at that exact coordinate, eliminating computational ambiguity. Once the key is struck, kinetic energy transfers from the mechanical hammer directly into the atomic lattice of the string. The AI must respect strict physical boundary conditions, specifically the string's tension, represented by T, and its linear mass density, represented by mu. These parameters dictate the velocity of the transverse wave. To determine the string's vibration, the system processes a partial differential wave equation, calculating how the mechanical wave propagates across the constrained length of the wire. The AI calculates the exact fundamental frequency and its harmonic overtones. It is not rendering pixels based on visual probability. It is executing a mathematical proof of acoustics. Follow the red arrows pointing from the mechanical keyboard down to the detailed oscilloscope waveform. Looking at this oscilloscope reading, we see the requirement for strict phase and frequency coupling. The visual motion and the auditory signal are locked together mathematically. Under this protocol, the AI operates entirely as a high-fidelity renderer for a deterministic Newtonian equation, bypassing the errors of a standard video generator. Applying this physics engine to a single piano string is straightforward, but scaling it to a crowd-level collaboration introduces a massive latency barrier. Sending raw audio back and forth to the cloud is too slow for real-time synchronization. This flow diagram illustrates the Sonora architecture, which solves the scaling issue by bypassing raw audio transmission entirely. The heavy audio processing never reaches the cloud. Instead, the client device runs a lightweight neural network to analyze the sound locally, extracting discrete musical feature vectors. These inputs are compressed into lightweight JSON telemetry packets containing precise metrics for rhythmic variance, harmonic consonance, and note density. The cloud-based state engine receives these packets and updates the environmental rules on a bar-by-bar basis. Operating on this macro control loop allows the system to avoid the standard latency associated with large language models. Distilling performance into these telemetry packets allows the system to scale to unlimited concurrent users without the latency that typically breaks digital collaboration. Once the system parses this telemetry, it faces a core computational challenge, teaching the AI to distinguish between an amateur timing error and an advanced, intentional creative expression. This scatterplot maps out a struggle signal. The system identifies this state when it detects high rhythmic variance combined with low harmonic consonance and a high density of notes. In response, the AI executes a stabilize protocol. It simplifies the backing track and enforces hard quantization, snapping erratic inputs to the grid. A flow signal emerges with low rhythmic variance and high harmonic consonance. The user is locked in. The AI initiates a withdraw action, introducing musical complexity and pulling away its foundational support to challenge the player. The expressive anomaly occurs when data shows high rhythmic variance, like intentional swing, paired with deep harmonic knowledge. Recognizing this intent, the AI executes a follow action. It turns off quantization entirely, allowing deliberate timing deviations to lead the ensemble. By mapping telemetry directly to human intent, the AI acts as a dynamic environmental conductor, prioritizing the human's creative logic over a binary set of rules. The architecture operates on 4 stages: predict and support, observe, and withdraw. In the final phase, the system executes a complete withdrawal. As the human achieves a self-sustaining flow state, the AI fades out its generative support, leaving the musician to carry the momentum independently. A system capable of continuous learning must recognize when to stop intervening, allowing the human to maintain the performance on their own. By grounding abstract musical expression in exact physical vectors and deterministic causality, we finally give AI the architectural framework to participate in the soul of human creativity, rather than just imitating its surface.